Hi, my name is Yeji Hong. I'm a PhD student in the Department of Civil Engineering at Purdue University. I want to introduce our study on encoder-decoder model for pavement subsurface crack detection and size estimation using GPR data. First, let's begin with the introduction. American public roadways face increased traffic volume, which results in poor conditions. Holistic understanding of pavement condition is crucial for effective infrastructure maintenance, repair, and rehabilitation strategies. Existing methods primarily focus on surface defects. However, vision-based techniques lack the ability to reveal underground pavement condition in the figure. Ground-penetrating radar is a non-destructive testing solution that uses electromagnetic waves to detect underground objects. GPR offers rapid and in-situ insight into pavement structures. Despite GPR's efficiency, automated interpretation of GPR data faces challenges, relying on human intervention due to difficulties in distinguish distress features from background. In addition, field collection of GPR data and distress detection model training is time-consuming and destructive. So, to solve these challenges, the paper proposes a novel method using an encoder-decoder model for detecting and quantifying pavement subsurface cracks using GPR data. Let us move on to the methodology. The first step is to create simulated data. In this paper, cubic Bezier curve is utilized to model the subsurface crack. By doing simulated B scans with varying trace and scan intervals, we got 4 simulated datasets. This study introduces an encoder-decoder model for crack detection and shape reconstruction. The model utilizes convolutional network for encoders, and the latent representations of B-scan images are concatenated and fed into the decoder. The outputs contribute to a fully connected layer for projection image reconstruction and center point and bounding box estimation. To validate the proposed method, 2 sets of experiments have been conducted using 4 datasets. The first set of experiments focuses on training and inference on the same dataset, while the second set assesses the generalization of the models by training and inference of different datasets. Let us move on to the experimental results. Table here shows average relative errors of dimension and center point estimation. The same dataset training and inference show no significant differences. Different datasets during training and inference increase dimension errors, but center point errors remain stable. Lower sampling rates sometimes yield better center point estimation results. Experiment 1 showed successful crack projection reconstruction, though some boundaries were blurry. Center point estimation was effective, but with a larger than actual radius. In experiment 2, performance degraded, and the model trained on lower sampling rates demonstrated better generalization to higher rates, emphasizing the crucial role of sampling rates in generalization ability. Here is the conclusion. The contribution of this study is threefold. Firstly, this study introduces an effective method for accurately locating and estimating the size of cracks using simulated GPR data extendable to 3D GPR. Secondly, this study demonstrates that the model trained with dense sampling adapts effectively to downsampling, potentially reducing data collection efforts in real-world field experiments. Lastly, this study provides insights into how Scan intervals and trace intervals affect the accuracy of crack size estimation and localization. Here is the reference, and thank you for your attention. If you have any question on this presentation, please email me via this email address. Thank you so much.